Good morning, our students, and welcome to this morning's discussion. Today, we'll be continuing our discussion on the introduction of a queen theory. In one of our previous classes, when we talked about T and Q theories, we began looking at what a Q is. And in the class, we did mention that Qs are waiting lines. And of course, the study of waiting line in a system is what we refer to as queuing theory. So anytime anybody talks about a queue and talks about the study of a queue, the person is talking about the waiting lines and equally talking about the study of how waiting lines form, how they function, and why they malfunction at times. That is what we do in queuing theory. There are some terms that are associated with queuing theories, which we want to look at this morning. And these terms associated with queuing theories are, we have one which we call the bulking. We have the bulking. We equally have another term which we call the reneging. And then we have another term which we call the jockeying. So we are going to explain these three terms as they concern queuing theory. What do we call barking in queuing theory? A barking is a situation where a customer arriving at a system for a service, on getting to their system, realizes that the system might waste his or her time before receiving service. And instead of joining the queue, decides to leave the system. That person or item that exhibited that character is said to have backed from that system. A situation, a customer which in the context could be a person, it could be an item, or it could be anything, arrives a system with intention to obtain a service. And on getting to that system, realizes that being in that system to have a turn for a service might take him or it a longer time, and decides to leave the system without receiving service, is said to have what? Backed the system. That is what the term backing means in queuing theory. Then, if you come to what backing, there are two types of backing. We have what we call forced backing. We have what we call a forced backing. And then we have what we call the unforced backing. Unforced backing. What do we call forced backing? What do we call unforced backing in queuing theory? Backing is said to be unforced if that customer, which could be a person, item, or object, arriving a system, realizes that waiting there might waste his or her time to get a service, decides on his or her own to leave the system. That act of leaving the system was not forced by any person. It's a decision by a customer to leave the system on the grounds that it is going to waste his time or her time waiting for his or her turn for a service. But in a situation where the person or item or object arriving the system realizes that the capacity of the system is filled up, that customer doesn't have a choice but to leave the system, but because there is no more provision for him to be accommodated in that particular system. And in that case, we now talk about forced backing. The leaving of that customer might not be necessarily location by his or her own intention, but on the grounds that the capacity of the system is already filled up, and there is no more provision for addition of an additional customer in that particular system. That person is having what we call first backing. And this first backing often occurs when we have a system that has what we call a finite queue length. Finite queue length in the sense that the system will say that the moment the number of the person in the system gets to this particular number, that system is no longer ready to admit another person or another customer in that system. So the person is meant to leave this system as long as that threshold of the queue length has been reached. That person is having what we call first backing. Then we now talk about what we call the reneging. In the reneging, what actually happens is a customer arrives a system and joins a queue. But after being in a queue for some times, realizes that it is going to waste his time or her time to have a turn for a service and then decides to leave that particular system. The difference between the barking and the reneging is that in the barking, the customer did not join the queue at all before taking a decision to leave the system or before being forced out of the system, depending on if it is on first barking or first barking. But in the reneging, the customer did not join the system at all. The customer joined the system, but after joining the system, decide to leave on the grounds that it is going to waste his or her time. In the backing, customer does not join the system at the queue at all. But then in the reneging, this customer joins the queue. But while in the queue, takes that decision either to leave the queue because it is going to waste his or her time. That is the difference between the backing and then the reneging. Both of them involves leaving the system. But one is leaving the system after joining the queue, but the other one is leaving the system after he has joined the queue. In the reneging, you join the queue, and after being in the queue, you leave the system. But in the backing, you do not join the queue at all before you leave the system. Then we now talk about what the jockeying. In the jockeying, as it concerns the queue in theory, a customer arrives the system. And then in that system, there are multiple queues, all of which are targeted in receiving the same service. And upon arriving at the system, the customer joins a particular queue. While being in that queue, he or she realizes that other queues or other lines are moving faster than the one he or she had earlier joined, and decided to now switch over to join any of the lines that are moving faster. In that case, we now say that the customer has joked. He has decided now to leave the line which he or she thinks is wasting much of his time to join other queues which he or she thinks is moving faster than the line where he or she is currently waiting for his or her own service. That is what we call jockeying. So when we are asked to explain these terms as it concerns what? Queuing theory, we tell them what backing is, arriving the system, not joining the system, leaves the system. It can be forced, it can be unforced. Reneging, arriving a system, joining the queue, while in the queue, taking the decision to leave the system on the grounds that it is going to waste his or her time. Jockeying, arriving a system where there are multiple queues, joining a particular queue, and after being at that particular queue, realizing that other queues are moving faster than the one he or she joined and decide to switch over to any of these queues that are moving faster. That is what we call the jockeying. So these are the explanation of these terms. Now let us now look at what we call the key metrics or measures of performance what in a queue. Permit me to clean here. we talk about the Q matrix of the performance of what of a queue. Talking about the key parameters that one looks at when you want to study the performance of what of a queue. Key performance measures. Key performance measures, or we can call it key performance matrix. Key performance matrix. We talk about number one. We talk about what we call the length of the queue. Talk about the length of the queue. Length of the queue. Length of the queue. Then number two, we talk about length of the system. Length of the system. Length of the system. Then number three, we talk about waiting time, or what we call average waiting time in the queue. Average waiting time in the queue. Average waiting time in the queue. Then we talk about number four, average waiting time in the system. Average waiting time in the system. Waiting time in the system. Then number five, we talk about what we call server utilization. Server utilization. Server utilization. Of course, we can decide to call this one average length of the queue. So I can add here average length of the queue, and equally add here average length of the system. Average length of the system. And what do we mean when we say average length of what? Of the queue? We are talking about the number of people who are on that queue on the average. Because if you come to a system, you find out that some people will be in a queue waiting for service, while others are already receiving service from that particular system. So there are two categories of people in that system. One, people who are on the queue waiting for service, and two, the others who are already receiving a service from that particular system. So when we talk about average length of the queue, we are interested on the number of people on the average who are waiting on the queue for their own turn for service. That is what we refer to as average length of the queue. But when we talk about average length of the system, we are talking about the number of the people on the average who are on that system, which of course in this context will include the people who are on the queue and equally people who are receiving service. So there is a difference when we talk about length of the queue and length of the system. And equally, there is a difference when we talk about average length of the queue and average length of the system. When we are talking about average length of the queue, our interest is number of the customers on the average who are on the queue waiting for the turn for their own service. But when we talk about average length of the system, we are talking about the number of people on the average who are on that system, which will include the people in the queue and equally the people who are already receiving service. That's what we mean by average length of the system. Then we now talk about average waiting time in the queue. We are now talking about the number of the time on the average that a customer spends on the queue waiting for a service. That is what we now talk about average waiting time. The total time of the average total time or the average time that a customer spends on the queue before it gets to his or her turn for service is what we refer to as average waiting time in the queue. Then when we talk about average waiting time in the system, we are talking about, on the average, the time that a customer spends in the system to get a service. So we are now talking about the time he spends while in the queue and plus the time he spends receiving service. That is what we are talking about, average waiting time in the system. Average waiting time in the system. Average waiting time in the system. Then when we now talk about the server utilization, we are now talking about the ratio of the arrival and then the service rates. The ratio of the arrival and then the service rates. Do remember that in our previous class when we looked at the introduction of queuing theory 1, we said that the arrivals in a system is always represented with a letter lambda. And then the service time or service rate is always represented with mu. So when we talk about the ratio of lambda and mu, we are talking about server utilization. So this server utilization is lambda all over what? All over mu. Where lambda is talking about the arrival rates and then the mu is talking about the service rates. So each time somebody wants to look at the performance of a particular queuing model in stochastic processes, one would want to obtain these parameters. And on these parameters now, one will now begin to assess how well or how poor that model has performed. Because the person will be able to look at the average length of the queue, talking about the total number of the people who are waiting, the average number of the people who are waiting in the queue. The person will be able to talk about the length of what? Of the system. Talk about now the average time that somebody is going to spend in the queue. Talk about the average number of time that the person is going to spend in the system. And talk about the server utilization before the person will now begin to make a statement about the performance of that particular queuing model. So anytime we are asked about the key performance metrics of key models, these are what we refer to as a key performance metrics. So you permit me to clean here while we talk about different types of queuing models. Different types of queuing models. So permit me to clean here. Different types of queuing models. Of course, when we talk about the queuing theory, we are talking about studying the waiting lines or how waiting lines form, then how they function and why they malfunction. And of course, you know that the arrival of customers to the system is in random manner. And then the service rate equally is also in random manner. So we are now talking about developing a model that will be able to capture the randomness of these arrivals at these service times. And the kind of model that we develop to capture these random nature of arrivals and then service times is what we call the queuing models. So these are models that we develop that will be able now to capture these random nature of arrivals and service times for us now to use these models now to be able to look at the key performances. And these queuing models are into classes. So we talk about types of queuing models. Talk about types of queuing models. Types of queuing models. Types of queuing models. Okay? And we are going to look at types of queuing models in terms of the following. We look at it now in terms of the number of servers. So we are going to look at it in terms of number one, number of servers. Number of servers. We now look at it now in terms of what we call the queue length. The queue length. And then we look at it now in terms of what we call types of population. Types of population. Types of population. So let us now begin by talking about types of queuing models in terms of number of servers. If you come to a system where, of course, there is only one server that is providing service to the customers, you'll find out that the number of servers in that particular system is 1. And then we call it a single server queuing model. Single server queuing model. Single server queuing model. Single server queuing model. Queuing model. That is to say, someone arriving in a particular bank and realizes that the only ATM machine, that there is only one ATM machine that attends to customers in that particular bank. You find out that the number of a server here, which in this context is that ATM machine, is 1. And in that case, we call it a single server queuing model. But then if someone arrives and then you have more than one servers there, where for instance, we have more than one ATM machines in that particular bank, we now call it a multiple server queuing model. Multiple server queuing model. Multiple server queuing model. And then when we now talk about queue length, of course, this queue length is classified into 2. We have what we call finite queue length and infinite queue length. And let me explain. What do we mean when we say that a queue length is finite? What we mean is this, that in that particular system, there is a threshold that people can be accommodated waiting for service. And anybody arriving in that system when that threshold has been reached is not allowed to join that system. In that case, we now say that that queuing length is finite. For instance, you have a mechanic shop where cars arrive for a service, and there are only 10 parking slots available in that particular workshop. Once 10 cars arrive and occupy these parking slots, no other car arriving is allowed to come into that place because that parking slot has been occupied. So the queue length here is 10 in number. Okay, that is what we refer to as the finite queue length. But queue length is said to be infinite if at any point in time a customer arrives, there is a provision for that person to join that particular system or to join that particular queue. It means that the queue length is infinite. And then, of course, we classify our queue model making use of this explanation. Therefore, you hear people say finite queue model and then infinite queue model. So when we are talking about finite queue model, we are talking about a model where the queue length has a threshold after which no customer is allowed to join the system or to join the queue. But when we talk about infinite queue model, we are talking about a queue model where the queue length allows anybody at any point in time arriving to join that particular system. And of course, some people can call it what? Finite queue model and infinite queue model, like I already had earlier mentioned. Okay? Then we now talk about looking at the type of what of a queue models now in terms of the population. When we talk about population now, we are talking about the customers that arrive for service. Then we can say that our population is finite when we narrow down the customer to a particular group of people. For instance, you come to a particular city, and then in that particular city, a customer or a mechanic might decide that he is only attending to people coming for a repair of their car, either from a particular institution. So any customer arriving that is not coming from that particular institution is not allowed to join that system. Not because the limit of the system has been exceeded, but on the grounds that the mechanic has defined his target population. But when another mechanic accepts anybody arriving for a repair of his or her car from anywhere, we now say that the population is infinite. So in that particular case, we can still talk about the finite population queuing model and then the infinite population queuing model. So these are different kinds of queuing models we have in terms of the number of servers, in terms of the queue length, and in terms of the types or of the nature of the population. Saying that there are different kinds of queuing models, it becomes necessary that an acronym be developed in order to describe these different queuing models. And then someone has helped us in this. So there is a person by name George Kendall, who of course has developed a format that we can use to describe these different queuing models. And then the format developed by the George Kendall is given as this. So it permits me to clean this. The format he gave is given as he has A slash S slash C slash K slash N and slash D. This is a format that George Kendall gave, with which we can describe the nature of our queuing model. A here stands for the distribution of arrival of customer in that particular system. Okay, the distribution that arrival time in that particular system, that this A stands for that. This S stands for the distribution of the service times in that particular system. And this C here stands for the number of servers in that particular system. So if this C takes 1, the queuing model will be described as a single server queuing model or a single server model. And if this C takes from 2 and above, we are going to describe it as a multiple queuing server model. So this K stands for the queue length. So when this K takes a number that is not infinite, we now talk about the finite queuing model. But when this K takes infinite value, then we now talk about infinite queuing model. So this N stands for what? For the population, where of course the population too can be finite and it can be infinite. And then this D stands for the queuing discipline. That is the rule or the principle of selecting the next customer to be attended to from the queue, which of course in our first introduction to the queuing model, we described different queuing discipline. One of which is what we call the first come, first serve, FIFS. We equally talked about what we call this first come, first serve can equally be called first in, first out, FIFO. We equally talked about what we call the last come, the first come, last served. Or it could be the last come, first served. And we equally talked about service being in random order, the cyro. These are different kinds of the queuing discipline, which one can easily see in our previous class on Introduction to Queuing Model, to Queuing Theory 1. So in the next class we are going to take in this queuing theory, we now begin to look at the different kinds of models. And when we are looking at different kinds of models, our interest should be for us to obtain the key metrics of measuring the performance of that queuing models. So we should be having the derivations for the average queue length, average queue length, talking about average length of the system, talking about average waiting time in the system, average waiting time in what? In the queue. We are going to have derivation for those things in each of the type of queuing model we are looking at. So thank you for giving us your audience today, this morning, as we plead with you to stay connected while we begin to gradually unfold teachings on queuing theories / queuing models. Thank you for your audience.